I was playing in the sandbox with my nephew when things got a little out of hand. Sand started flying everywhere. And of course, one tiny grain found its way into my eye. Did I care about the missing sand from the box? Not at all. It was nothing compared to the whole sandbox. But those grains in my eye? Just one or two, yet impossible to ignore. Some chemical reactions are like that. The amount of reactant that converts to product is so small that we can ignore the loss of reactants. But that tiny bit of product, it's something instead of nothing. And sometimes that makes all the difference. This is Real Chem. When solving equilibrium problems, we don't always need to wrestle with complicated algebra. Sometimes we can keep things simple. If a reaction has a very small equilibrium constant, only a tiny fraction of reactants turn into products. So little that the initial amount of reactants stays practically the same. That lets us make a useful assumption. The reactant concentrations at equilibrium are nearly identical to what they were before the reaction even started. Let's see how this trick makes equilibrium calculations much easier. Let's consider this reversible reaction where yellow molecules convert to red. If the equilibrium constant K is very small, say K equal 1 by 10 to the power -6, then at equilibrium, the system will consist almost entirely of yellow molecules, with only a few red molecules mixed in. Visually, it might look something like this. That means the yellow molecule is the majority species. It dominates at equilibrium. The red molecule, on the other hand, is the minority species. There's only a tiny amount of it. Let's start with a high concentration of yellow molecules, 0.5 molar, with no red molecules at all. How can we figure out the concentrations at equilibrium? We need a way to connect these values to our initial concentrations. A great tool for this is an ice table. The top row shows the initial amounts. The bottom row gives the equilibrium amounts. And in between, we track the changes that happen as the system moves toward equilibrium. First, we fill in our initial values. For the change row, we use X to represent the amount of yellow molecules that convert to red. Since the reaction has one-to-one stoichiometry, every time we lose some yellow molecules, minus X, we gain an equal number of red molecules, plus X. Adding the initial and change rows gives us the equilibrium concentrations. From here, we can use the equilibrium expression, K. One key point to remember, the equilibrium expression applies only to equilibrium concentrations. It cannot be used with initial concentrations or any other values. Now, we can substitute the equilibrium concentrations into our K expression. The ice table helped us by expressing everything in terms of a single variable, X. This gives us one equation and one unknown. We can solve for X to find our concentrations. This approach works for any value of K, but when K is small, we can make things even easier. If K is small, that means only a tiny fraction of yellow molecules converted to red, so the value of X will be small. Of course, just saying something is small doesn't mean that much unless we compare it to something. Here, we mean X is small compared to the amount of yellow molecules we started with. So X is small compared to 0.5. To express this mathematically, we use a double less than sign to show that X is much smaller than 0.5. So small that we can ignore it when subtracting from 0.5. We can adjust our ice table to reflect this approximation, which makes our equilibrium expression much simpler, because now we can ignore X in the denominator. Solving this equilibrium expression for X gives us 5.0 times 10 to the power of -7. We can confirm that this number is much smaller than 0.5, just like we assumed. Now that we know X, we can find the equilibrium concentrations from the bottom row of the ice table. At equilibrium, the concentration of yellow is 0.5 molar, and the concentration of red is 5.0 times 10 to the power of -7 molar. That was a good approach, but there's another way to look at it, one that might feel more intuitive. Let's go back to our original goal. We started with a known initial concentration of yellow molecules, and we want to use the equilibrium expression to find the concentrations at equilibrium. Because K is small, we can assume that only a tiny amount of yellow molecules convert to red by the time equilibrium is reached. That means the equilibrium concentration of yellow is essentially the same as its initial concentration, 0.5 molar. We can substitute the equilibrium concentration of this majority component directly into the equilibrium expression. This lets us solve for the equilibrium concentration of our minority component, red, at equilibrium. This comes out to be 5.0 times 10 to the power of negative 7 molar, the same value we got before. Why? Because both approaches rely on the same key idea. The amount of yellow that converted to red was so small that the equilibrium concentration of yellow is still effectively 0.5 molar. Many real-world reactions, especially in acid-base and solubility chemistry, have small equilibrium constants K. As we explore these topics, knowing how to take advantage of the magnitude of K will be key to building our intuition for these systems. It's just like that grain of sand from the sandbox. I didn't need to count every grain in the box. I only cared about the tiny amount in my eye. For reactions with small K, we don't have to track every tiny change in reactant amounts. Instead, we focus on the small amount of product that forms, making equilibrium calculations much easier.